Hi everyone, let me continue with the book on page 119. By convention, argv bracket 0 is the name by which the program was invoked. So argc is at least 1. In the example above, argc is 3 in argv bracket 0. argv bracket 1 and argv bracket 2 are equal hello and world. Respectively, the first real argument is argv bracket 1 and the last is argc minus 1. If argc is 1, there are no command line arguments after the program name. This is shown in equal. Since argv is a pointer to an array of pointers, there are several ways to write this program that involve manipulating the pointer rather than indexing an array. Let us show two variations. Since argv is a pointer to the beginning of the array of argument strings, incrementing it by 1 parentheses plus plus argv makes it point at the original argv bracket 1 instead of argv bracket 0. Each successive increment moves it along to the next argument. Asterisk argv is then the pointer to that argument. At the same time, argc is decremented when it becomes 0. There are no arguments left to print. Alternatively, this version shows that the format argument of printf can be an expression just like any of the others. This usage is not very frequent, but worthy remembering. In the second example, let us make some enhancements to the pattern finding program from chapter 4. If you recall, we wired the search pattern deep into the program, an obviously unsatisfactory arrangement following the lead of the Unix utility grep. Let us change the program so the pattern to be matched is specified by the first argument on the command line. The basic model can now be elaborated to illustrate further pointer constructions. Suppose we want to allow two optional arguments. One says print all lines except those that match the pattern. The second says precede each printed line with its line number. A common convention for C programs is that an argument beginning with a minus sign introduces an optional flag or parameter. If we choose -x for except to signal the inversion and -m number to request line numbering, then the command with the input should produce to output. Optional arguments should be permitted in any order, and the rest of the program should be insensitive to the number of arguments which were actually present. In particular, the call to index should not refer to argv bracket 2 when there was a single flag argument to argv bracket 1. When there wasn't. Furthermore, it is convenient for users if option arguments can be concatenated as in like this. Here is the program like this goes. Okay, argv is incremented before each optional argument and argc decremented if there are no errors. At the end of the loop, argc should be 1 and asterisk rv should point at the pattern. Notice that the asterisk plus plus argv is a pointer to an argument string. Parenthesis asterisk plus plus argv bracket 0 is its first character. The parentheses are necessary, for without them, the expression would be asterisk plus plus argv bracket 0, which is quite different and wrong. An alternate valid form would be asterisk asterisk plus plus argv. Exercise 5 middle score 7. Write the program at which evaluates a reverse Polish expression from the command line. For example, evaluates to multiply parentheses 3 plus 4. Exercise 5 middle score 8. Modify the programs in tab and d tab written as exercises in chapter 1 to access a list of tab stubs as arguments. Use the normal tab settings if there are no arguments. Exercise 5 middle score 9. Extend n tab and d tab to accept a shorthand. To mean tabs, stubs, RV, and columns starting at column M, choosing convenient for the user default behavior. Exercise 5 middle score 10. Write the program tail, which prints the last n lines of its input. By default, n is 10, let us say, but it can be changed by an optional argument so that prints the last n lines. The program should behave rationally no matter how unreasonable the input or the value of n. Write the program so it makes the best use of the available storage. Lines should be stored as in sort, not in a two-dimensional array of fixed size. 5.12 Pointers to functions. In C, a function itself is not a variable, but it is possible to define a pointer to a function, which can be manipulated passed to functions, placed in arrays, and so on. We will illustrate this by modifying the sorting produce written earlier in this chapter so that if the optional argument -n is given, it will sort the input lines numerically instead of lexicographically. A sort often consists of 3 parts: a comparison, which determines the ordering of any pair of objects; an exchange, which reverses their order; and a sorting algorithm, which makes comparisons and exchanges until the objects are in order. The sorting algorithm is independent of the comparison and exchange operations. So by passing different comparison and exchange functions to it, we can arrange to sort by different criteria. This is the approach taken in our new sort. A lexicographic comparison of 2 lines is done by striking and swapping by swap as before. We will also need a routine NUMCMP which compares 2 lines on the basis of numeric value and returns the same kind of condition indication as striking does. These 3 functions are declared in main, and pointers to them are passed to sort. Sort, in turn, causes the functions fetch the pointers. We have skimmed on error processing for arguments, so as to concentrate on the main issues. CAM, NUM, CMP, and swap are addresses of functions. Since they are known to be functions, the ampersand operator is not necessary. In the same way that it is not needed before an array name, the compiler arranges for the address of the function to be passed. The second step is to modify sort. The declarations should be studied with the same care. The declarations should be studied with some care. Says that camp is a pointer to a function that returns an int. The first set of parentheses are necessary. Without them, would say that camp is a function returning a pointer to an int, which is quite a different thing. The use of camp in the line is consistent with the declaration camp is a pointer to a function. Asterisk camp is the function and is the call to it. The parentheses are needed so the components are correctly associated. We have already shown camp, which compares two strings. Here is NUM CMP, which compares two strings on a leading numeric value. Final step is to add the function swap, which exchanges two pointers. This is adapted directly from what we presented earlier in the chapter. There are a variety of other options that can be added to the sorting program. Some make challenging exercises. Exercise 5 score 11 modify sort to handle a R flag, which indicates sorting in reverse decreasing order. Of course, R must work with N. Exercise 5 score 12 add the option F to fold upper and lower keys together, so that case distinctions are not made during sorting. Upper and lower case data are sorted together so that lowercase a and uppercase a appear adjacent, not separated by entire keys of the alphabet. Exercise 5 score 13. Add the dictionary order option, which makes comparisons only on letters, numbers, and blanks. Make sure it works in conjunction with F. Exercise 5 score 14. Add a field handling capability so sorting may be done on fields within lines, each field according to an independent set of options. The index for this book was sorted with DF for the index category and N for the page numbers. Chapter 6 Structures. A structure is a collection of one or more variables, possibly of different types, grouped together under a single name for convenient handling. Structures are called records in some languages, most notably Pascal. The traditional example of a structure is a payroll record. An employee is described by a set of attributes such as name, address, social security number, salary, etc. Some of these in turn could be structures. A name has several components, as does an address and even a salary. Structures help to organize complicated data, particularly in art programs, because in many situations they permit a group of related variables to be treated as a unit instead of as separate entities. In this chapter, we will try to illustrate how structures are used. The programs we will use are bigger than many of the others in the book, but still of modest size. 6.1 Basics. Let us revisit the data conversion routines of Chapter 5. A date consists of several parts, such as the day, month, and year, and perhaps the day of the year and the month name. These 5 variables can all be placed into a single structure like this. The keyword struct introduces a structure declaration, which is a list of declarations enclosed in braces. An optional name called a structure tag may follow the word struct. As with date here, the tag names this kind of structure and can be used subsequently as a shorthand for the detailed declaration. The elements or variables mentioned in a structure are called members. A structure member or tag or an ordinary non-member. A variable can have the same name without conflict, since they can always be distinguished by context. Of course, as a matter of style, one would normally use the same names only for closely related objects. The right phrase that terminates a list of members may be followed by a list of variables, just as for any basic type, that is syntactically analogous to, in the sense that each statement declares X, Y, and Z to be variables of the named type and causes space to be allocated for them. A structure declaration that is not followed by a list of variables allocated is non-storage. It merely describes a template or the shape of a structure. If the declaration is tagged, however, the tag can be used later in definitions of actual instances of the structure, for example, given the declaration of date above. Defines a variable D, which is a structure of type date. An external or static structure can be initialized by following its definition with a list of initializers for the components. A member of a particular structure is referred to in an expression by a construction of their form. The structure member operator point connects the structure name and the member name to set leap from the date in structure D, for example, or to check the month's name, or to convert the first character of the month's name to lowercase. Structures can be nested. A parallel record might actually look like. The person structure contains 2 deities. If we declare AMP as like this, then this word refers to the month of birth. The structure member operator point associates left or right. 6.2 Structures and Functions. There are a number of restrictions on C structures. The essential rules are that the only operations that you can perform on a structure are take its address with ampersand and access one of its members. This implies that structures may not be assigned or copied as a unit, and that they cannot be passed to or returned from functions. These restrictions will be removed in forthcoming versions. Pointers to structures do not suffer these limitations. However, substructures and functions do work together comfortably. Finally, automatic structures like automatic arrays cannot be initialized. Only external or static structures can. Let us investigate some of these points by rewriting the date conversion functions of the last chapter to use structures. Since the rules prohibit passing a structure to a function directly, we must either pass the components separately or pass a pointer to the whole thing. The first alternative uses day of year as we wrote in chapter 5. The other way is to pass a pointer if we have declared higher date as and rewritten, we can then say to pass a pointer to higher date to day of year. The function has to be modified. The function has to be modified because its argument is now a pointer rather than a list of variables. The declaration says that PD is a pointer to a structure of type date. The notation exemplified by is new. If P is a pointer to a structure, then refers to the particular member. The operator arrow is a minus sign followed by. Since PD points to the structure, the year member could also be referred to as by pointers to structures are so frequently used that the arrow notation is provided as a convenient shorthand. The parentheses are necessary in parentheses asterisk PD point year because the precedence of the structure member operator dot is higher than asterisk. Both arrow and dot associate from left to right, so like this or this. For completeness, here is the other function must be rewritten to use the structure. The structure operators arrow and dot together with parentheses for argument list and bracket for subscripts are at the top of the precedence hierarchy and thus bind very tightly. For example, given the declaration like this, then plus plus p arrow x increments x not p because the implied parenthesization is plus plus parentheses p arrow x. Parentheses can be used to alter the bending. Parentheses plus plus p arrow x increments p before accessing x, and parentheses p plus plus arrow x increments p afterward. This last set of parentheses is unnecessary. Why? In the same way, asterisk p arrow y fetches whatever y points to. Asterisk p arrow y plus plus increments y after accessing whatever it points to, just like asterisk s plus plus. Parentheses asterisk p arrow y plus plus increments whatever y points to, and asterisk p plus plus arrow y increments p after accessing whatever y points to. 6.3 Arrays of structures. Structures are especially suitable for managing arrays of related variables. For instance, consider a program to count the occurrences of each C keyword. We need an array of character strings to hold the names and an array of integers for the counts. One possibility is to use two parallel arrays, keyword and key count, as in this. But the very fact that the arrays are parallel indicates that a different origin organization is possible. Each keyword entry is really a pair. And there is an array of pairs. The structure declaration like this defines an array key tab of structures of this type and allocated storage to them. Each element of the array is a structure. This could also be written. Since the structure key tab actually contains a constant set of names, it is easiest to initialize it once and for all when it is defined. The structure initialization is quite analogous to earlier ones. The definition is followed by a list of initializers enclosed in braces. The initializers are listed in pairs corresponding to the structure members. It would be more precise to enclose initializers for each row or structure in braces. It's in this, but the inner braces are not necessary when the initializers are simple variables or character strings. And when all are present, as usual, the compiler will compute the number of entries in the array key tab of initializers are present and the bracket is left empty. The keyword counting program begins with the definition of key tab. The main routine reads the input by repeatedly calling a function getWord that fetches the input one word at a time. Each word is looked up in key tab with a version of the binary search function that we wrote in chapter 3. Of course, the list of keywords has to be given in increasing order for this to work. We will show the function getWord in a moment. For now, it serves to say that it returns letter each time it finds a word and copies the word into its first argument. The quantity in keys is the number of keywords in key tab. Although we could count this by hand, it is a lot easier and safer to do it by machine, especially if the list is subject to change. One possibility would be to terminate the list of initializers with a null pointer, then loop along key tab until the end is found. But this is more than is needed, since the size of the array is completely determined at compile time. The number of entries is just. C provides a compile time unary operator called sizeOf, which can be used to compute the size of any object. The expression is an integer equal to the size of the specified object. The size is given in unspecified units called bytes, which are the same size as a char. The object can be an actual variable or array or structure, or the name of a basic type like int or double, or the name of a derived type like a structure. In our case, the number of keywords is the array size divided by the size of one array element. This computation is used in a hash define statement to set the value of n keys. Now for the function getWord, we have actually written a more general getWord than is necessary for this program, but it is not really much more complicated. GetWord returns the next word from the input, where a word is either a string of letters and digits beginning with a letter or a single character. the type of the object is returned is a function value. It is latter if the token is a word, EOF for end of file, or the character itself if it is non-alphabetic. Like this word. GetWord uses the routine sketch and engage, which we wrote in chapter 4. When the collection of an alphabetic token stops, GetWord has gone one character too far. The call to engage pushes that character back on the input for the next call. GetWord calls type 2 and determining the type of each individual character of input. Here is a version of the asker alphabet only. The simply constants letter and digit can have any values that do not conflict with non-alphanumeric characters and EOF. The obvious choices are GetWord. Like this, GetWord can be faster if calls to the function type are replaced by references to an appropriate array type break it. The standard C library provides macro called is alpha and its digit which operate in this manner. Exercise 6 middle score 1 makes this modification to GetWord and measure the change in speed of the program. Exercise 6 middle score 2 write a version of type which is independent of character set. Exercise 6 middle score 3 write a version of the keyword counting program which does not count occurrences contained within quoted strings. 6.4 Pointers to structures. To illustrate some of the considerations involved with pointers and arrays of structures, let us write the keyword counting program again, this time using pointers instead of array indices. The external declaration of key tab need not change, but main and binary do need modification. There are several things worthy of note here. First, the declaration of binary must indicate that it returns a pointer to the structure type key instead of an integer. This is declared both in main and in binary. If binary finds the word, it returns a pointer to it. If it fails, it returns null. Second, all the accessing of elements of key tab is done by pointers. This causes one significant change in binary. The computation of the middle element can no longer be simply, because the addition of two pointers will not produce any kind of a useful answer, even when divided by 2, and in fact is illegal. This must be changed to like this, which sets mid to point to the element halfway between low and high. You should also study the initializers for low and high. It is possible to initialize a pointer to the address of a previously defined object. That is precisely what we have done here. In main, we wrote, if P is a pointer to a structure, any arithmetic on P takes into account the actual size of the structure. So P++ increments P by the correct amount to get the next element to the array of structures. But don't assume that the size of a structure is the sum of the sizes of its members, because of alignment requirements for different objects. There may be holes in the structure finally and aside on program format when a function returns a complicated type as in. The function name can be hard to see and defined with a text editor. Accordingly, an alternate style is sometimes used. This is mostly a matter of personal taste. Pick the form you like and hold to it. 6.5 Self-Referential Structures. Suppose we want to handle the more general problem of counting the occurrences of all the words in some input. Since the list of words isn't known in advance, we can conveniently sort it and use a binary search. If we can do a linear search for each word as it arrives to see if it is already being seen, the program would take forever. More precisely, its expected running time would grow quadratically with the number of input words. How can we organize the data to cope efficiently with a list of arbitrary words? One solution is to keep the set of words seen so far sorted at all times by placing each word into its proper position in the order as it arrives. This shouldn't be done by shifting words in a linear array, though that also takes too long. Instead, we will use a data structure called a binary tree. The tree contains one node per distinct word. Each node contains, like this, no node may have more than 2 children. It may have only 0 or 1. And nodes are maintained so that at any node the left subtree contains only words which are less than the word at the node, and the right subtree contains only words that are greater. To find out whether a new word is already in the tree, one starts at the root and compares the new word to the word stored at that node. If they match, the question is answered affirmatively. If the new word is less than the tree word, the search continues at the left child. Otherwise, the right child is investigated. If there is no child in the required direction, the new word is not in the tree. And in fact, the proper place for it to be is the missing child. This search process is inherently recursive. Yeah. Since the search from any node uses the search from one of its children, accordingly, recursive routines for insertion and printing will be most natural. Go back to the description of a node. It is clearly a structure with 4 components. Like this. This recursive declaration of a node might look chintzy, but it is actually quite correct. It is illegal for a structure to contain an instance of itself, but declare is left to be a pointer to be a node, not a node itself. The code for the whole program is surprisingly small, giving a handful of supporting routines that we have already written. These are get word to fetch each input word and a log to provide space for squaring the words away. The main routine simply reads words we with get word and installs them in the tree with tree, like this. Tree itself is straightforward. A word is presented by main to the top level, the root of the tree. At each stage, that word is compared to the word already stored at the node, and is percolated down to either the left or right subtree by a recursive call to tree. Eventually, the word either matches something already in the tree, in which case the count is incremented, or a new pointer is encountered, indicating that a node must be created and added to the tree. If a new node is created, tree returns a pointer to it, which is installed in the parent node. Storage for the new node is fetched by a routine TLOC, which is an adaptation of the alloc we wrote earlier. It returns a pointer to a free space suitable for holding a tree node. We will discuss this more in a moment. The new word is copied to a hidden place by strcsave. The count is initialized and the two children are made null. This part of the code is executed only at the edge of the tree. When a new node is being added, we have, unwisely for a production program, emptied error checking on the values returned by strcsave in a TLOC. Tree print prints the tree in left subtree order. At each node, it prints the left subtree, all the words less than this word, then the word itself, then the right subtree, all the words greater. If you feel shaky about recursion, draw yourself a tree and print it with tree print. It's one of the cleanest recursive routines you can find. A practical note: if the tree becomes unbalanced because the words don't arrive in random order, the running time of the program can grow too fast. In the worst case, if the words are already in order, this program does an expensive simulation of linear search. There are generalizations of the binary tree, notably 2 to 3 trees in AVL trees, which do not suffer from this worst case behavior, but we will not describe them here. Before we leave this example, it is also worthy a brief digression on a problem related to storage allocators. Clearly, it is desirable that there be only one storage allocator in the program, even though it allocates different kinds of objects. But if one allocator is to process requests for, say pointers to char and pointers to struct T-nodes, two questions arise. First, how does it meet the requirement of most real machines that objects of certain types must satisfy alignment restrictions? For example, integers often must be located on even addresses. Second, what declarations can cope with the fact that a lock necessarily returns different kinds of pointers? Alignment requirements can generally be satisfied easily, at the cost of some wasted space, merely by ensuring that the allocator always returns a pointer that meets all alignment restrictions. For example, on the PDP-11, it is sufficient that a lock always return an even pointer, since any type of object may be stored at an even address. The only cost is a wasted character on odd length request. Similar actions are taken on other machines, thus the implementation of a lock may not be portable, but the usage is. The lock of Chapter 5 does not guarantee any particular alignment. In Chapter 8, we will show how to do the job right. The question of the type declaration for a lock is a fixing one for any language that takes its type checking seriously. In C, the best procedure is to declare that a lock returns a pointer to char, then explicitly course the pointer into the desired type with a case. That is, if P is declared as char *P, then like this, converts it into a T0 pointer in an expression. Thus, TLOG is written like this. This is more than is needed for current compilers, but it represents the safest course for the future. Exercise 6, middle score 4. Write a program which reads a C program and prints in alphabetical order each group of variable names which are identical in the first 7 characters, but different somewhere thereafter. Make sure that 7 is a parameter. Exercise 6, middle score 5. Write a basic cross-referencer, a program which prints a list of all words in a document, and for each word a list of the line numbers on which it occurs. Exercise 6, middle score 6. Write a program which prints the distinct words in its input sorted into decreasing order of frequency of occurrence. Precede each word by its count. 6.6 Table Lookup. In this section, we will write the innards of a table lookup package as an illustration of more aspects of structures. This code is typical of what might be found in the simple table management routines of a macroprocessor or a compiler. For example, consider the C# define statement when a line like is encountered. The name S and the replacement text 1 are stored in a table. Later, when the name S appears in a statement like it must be replaced by 1, there are 2 major routines that manipulate the names and replacement text. Install records the name S and the replacement text T in the table. S and T are just character strings. Lookup searches for S in the table and returns a pointer to the place where it was found or null. If it wasn't there, the algorithm used is a hash search. The incoming name is converted into a small positive integer, which is then used to index into an array of pointers. An array element points to the beginning of a chain of blocks describing names that have that hash value. It is null if no names have hashed to that value. A block in the chain is a structure containing pointers to the name, the replacement text, and the next block in chain. A new next pointer marks the end of the chain. The pointer array is just like this words. The hashing function, which is used by both lookup and install, simply adds up the character values in the string and forms the remainder modulo the array size. This is not the best possible algorithm, but it has the merit of extreme simplicity. The hashing procedures a starting index in the array hash tab. If the string is to be found anywhere, it will be in the chain of blocks beginning there. The search is performed by lookup. If lookup finds the entry already present, it returns a pointer to it. If not, it returns null. Install uses lookup to determine whether the name being installed is already present. If so, the new definition must supersede the old one. Otherwise, a completely new entry is created. Install returns null if, for any reason, there is no room for a new entry. Receive merely copies the string given by its argument into a safe place, obtained by call on a log. We showed the code in Chapter 5. Since calls to a log and free may occur in any order, and since alignment matters, the simple version of a log in Chapter 5 is not adequate here. See Chapter 7 and 8. Exercise 6, middle score 7. Write a routine which will remove a name and definition from the table maintained by lookup and install. Exercise 6, middle score 8. Implement a simple version of the hash-defined processor suitable for use with C programs based on the routines of this section. You may also find Gauge and Engage helpful. 6.7 feels when storage space is at a premium. It may be necessary to pack several objects into a single machine word. One especially common use is a set of single-bit flags in applications like compiler symbol tables. Externally imposed data formats such as interfaces to hardware devices also often require the ability to get at pieces of a word. Imagine a fragment of a compiler that manipulates a symbol table. Each identifier in a program has certain information associated with it. For example, whether or not it is a keyword, whether or not it is external and or static, and so on. The most compact way to encode with such information is a set of 1-bit flag in a single char or int. The usual way this is done is to define a set of masks corresponding to the relevant bit positions, as in like this. The numbers must be a power of 2. Then accessing the bits becomes a matter of bit fitting, with the shifting, masking, and complementing operators, which were described in Chapter 2. Certain items appear frequently. Like this turns on the external and static bits in flags, while turns them off, and it's true if both bits are off. Although these items are readily mastered, as an alternative, C offers the capability of defining and accessing fields within a word directly rather than a bitwise logical operators. A field is a set of adjacent bits within a single end. The syntax of field definition and access is based on structures. For example, the symbol table hash defines above could be replaced by the definition of 3 fields. This defines a variable called flags that contains 3 one-bit fields. The number following the column represents the field width in bits. The fields are declared unsigned to emphasize that they really are unsigned quantities. Individual fields are referenced as flags point dot is underscore keyword extractors. Just like other structure members, fields behave like small unsigned integers in any and may participate in arithmetic expressions just like other integers. Thus, the previous examples may be written more literally as to turn the bits on, to turn them off, and to test them. A field may not overlap an end boundary. If the width would cause this to happen, the field is aligned at the next end boundary. Fields need not be named unnamed fields. A column and width only are used for padding. The special width 0 may be used to force alignment at the next end boundary. There are a number of caveats that apply to fields. Perhaps most significant fields are assigned left to right on some machines and right to left on others, reflecting the nature of different hardware. This means that although fields are quite useful for maintaining internally defined data structures, the question of which end comes first has to be carefully considered when picking apart externally defined data. Other restrictions to bear in mind: fields are unsigned. They may be stored only in ends or equivalently unsigned. They are not arrays. They do not have addresses, so the ampersand operator cannot be applied to them. Okay, here I'm gonna have a break.